Tensor calculus is one of those topics that sounds intimidating the first time you hear it, almost like something only theoretical physicists or advanced mathematicians dare to touch. But once you break it down to everyday ideas, you'll see that it's built on simple concepts you already know. At its heart, tensor calculus is nothing more than a powerful language for describing how things change, twist, stretch, or move in spaces that may be curved, multidimensional, or constantly evolving. To understand why tensor calculus exists, we need to go back to a basic idea. Different viewpoints give different measurements. If you're standing on a moving train and drop a ball, you see it fall straight down. If someone outside watches, they see it fall along a curved path because the train is moving. Both views are correct, just expressed in different reference frames. Tensor calculus is the tool that ensures the laws of physics still make sense no matter who is observing or how they're moving. Think of a tensor as a very smart container for information. It's like a data structure designed for the universe itself. A regular number tells you how much. A vector tells you how much and in what direction. A tensor can tell you how much, in which direction, how it changes depending on where you look, and how it interacts with other things around it. It's like an upgraded version of vectors that can describe more complex relationships, such as how a piece of material bends, how gravity curves space, or how stresses flow through a 3D object. Tensor calculus specifically deals with how these tensors behave when things move or when your viewpoint changes. This is incredibly important because most real-world systems don't sit still. A river flows, planets orbit, rockets accelerate, and spacetime itself curves under the weight of stars. Tensor calculus provides a rulebook for describing all this in a consistent way. A helpful analogy is a map printed on a flexible sheet of rubber. Imagine drawing a square on the sheet. Now stretch the sheet unevenly. The square becomes distorted. It might twist, bulge, or stretch differently in various directions. If you want to describe exactly how that shape changed, you need a tool that can capture the stretching behavior in every direction at once. That tool is a tensor. Tensor calculus, then, is the technique for studying how these distortions vary across the entire sheet, point by point. Another example comes from everyday engineering. Think about pressing your thumb into a memory foam pillow. The foam doesn't just compress downward, it also squeezes outward, shifts sideways, and rearranges its internal structure. Engineers need a way to describe the forces at each tiny point inside the foam, including how those forces push or pull in several directions at the same time. Again, tensors provide the natural language for this. The real magic of tensor calculus shows up when we talk about curved spaces. Our normal intuition is based on flat surfaces, like graph paper. But many things in physics occur on surfaces that behave more like bent or curved landscapes. The surface of Earth, for example, is curved. Space-time in Einstein's theory of relativity is curved as well, and the shape of that curvature is what we perceive as gravity. You need tensors to describe motion on curved surfaces because vectors, angles, and distances behave differently from point to point. Tensor calculus ensures that you can still measure change consistently even when the space itself bends. One of the key challenges in curved spaces is that directions change depending on where you stand. If you walk straight north on Earth, the direction of east slowly rotates beneath your feet. Tensor calculus handles these shifting directions with a set of rules that carefully track how orientation changes as you move. This allows you to express physical laws, like the motion of planets, without depending on a particular coordinate system or viewpoint. This independence from coordinates is one of the biggest strengths of tensor calculus. It guarantees that the laws of nature remain true regardless of how you choose to describe them. You can use different units, rotate your axes, or move at a constant speed, and the underlying physical laws stay the same. Tensors are built to transform correctly when you change your viewpoint. They carry all the information needed to adapt automatically. In physics, this becomes crucial. For example, in general relativity, gravity isn't seen as a force but as the bending of space-time. Objects simply follow the straightest possible path in that curved geometry. Tensor calculus provides the toolkit to define these paths, quantify the curvature, and understand how matter and energy shape the universe. But tensor calculus isn't just for cosmology. It shows up in robotics when calculating how forces move through mechanical arms, in computer graphics when simulating realistic cloth, smoke, or water, in medicine when mapping the fibers inside the human brain, and in machine learning when working with multidimensional data structures.
Even GPS relies indirectly on tensor calculus because it depends on relativistic corrections derived from curved spacetime.
At its core, tensor calculus is about describing change in a consistent, universal way, no matter where you are, how you're moving, or what shape the space around you takes. It's the mathematical backbone that lets us study a universe that bends, flows, rotates, and evolves. And while the formal details can become complex, the idea is beautifully simple. Give me any viewpoint, any coordinate system, any motion, and tensors will express the laws of nature without breaking. That is the true power of tensor calculus.